Awesome. Welcome everybody to this week's GOCC. Before we get started with the talk, I just want to remind everybody of our community statement. And so we follow three overarching guidelines. And so the first one is we're all learning. So we encourage you to ask questions and share things that you know. But with that also give space, take space. And so some of us are more chatty than others. And so, just be mindful of the amount of space that we take. And if you are somebody that's shy, I really encourage you to open up a little bit and feel free to ask any questions because your voice is just as valid. The second one is everyone has something to contribute. So we all come from different areas of combinatorics. And so we can make connections and we'd love to hear them. And then the last one is no one has all the answers, not even the speaker. So the speaker will make their best effort to answer, but maybe somebody else knows the answers or we can figure it out together. And then the last one that I kind of want to add is to just be mindful with muting and unmuting yourself. So I'm going to request that everybody mutes themselves during the talk. Unless you have a question, then feel free to unmute. Also feel free to use the chat function. And so Jodi, I don't know, can you see the chat or should I interrupt and kind of?
I can, but it would probably be nice if you notice something before I do.
Okay.
And say something about it.
Sounds good. So then Alex and I will keep track of the chat and kind of.
Yeah, I'd probably even encourage Jodi not to look at the chat too much because sometimes people will have like conversations that are answered and stuff. So we'll take a look and tell you if there's a question on there. I know as a speaker before, I've been distracted by it, and it's just like people answering each other's questions or making jokes.
Yeah. So we'll keep track of that. And with that, it is my pleasure to introduce Jodie Mcwhirter from Washington University in St. Louis, who I just found out is co-advised by Laura Escobar and John Sheresian. So that's exciting. I met Jodi at SF State when I was a finishing master's student, and now it's very nice to invite her to the GOCC. And so she'll be telling us about Ehrhart quasi-polynomials of Coxeter permutahedra. So let's welcome Jodi.
Yeah, and thanks for the invitation. I'm excited to share this, what I think is a pretty fun project with more people. And yeah, I'll echo what Andres and Alex said. Like, if you guys have questions, feel free to interrupt me. Feel free to send stuff in the chat. I know Andres at least knows some stuff about Ehrhart theory, so he might even be able to answer some questions as well. And so, yeah, so this talk is a recently published paper that's based on my master's thesis. And so here at the bottom, I've got a picture at my graduation with Matt and Federico. But yeah, so I imagine some of you know a lot of the words that are in my talk title, but it's always entertaining to me that a lot of people will look at this and are like, well, I know of. And so hopefully by the end of this talk, you'll have a better idea what each of these words mean. To give you a little bit of a preview, the kind of goal is that we have these objects, which are these permutahedra, and they're special polytopes that a lot of people are interested in for various reasons. And the Ehrhart quasi-polynomial is describing the discrete volume of these things. So volume is something that a lot of people want to know for various reasons. Most of the time when you hear volume, you'll think of the continuous version of volume. And what I'm looking at is the discrete version of the volume. And so that's the integer point count of these polytopes. And so to get started, we'll go through a couple definitions here. And so our main players are these convex polytopes. So you have a not working pen. That's okay. We're gonna try this out with my finger instead of my pen, so this will be interesting. But convex polytope, you take some collection of points, and then we kind of put the rubber band type thing around it, so we get something like this. Or in 3 dimensions, something similar. Main point is that it's convex, flat sides, flat faces, and all that. And then, like I said, we're going to be looking at the discrete volume, so the number of integer points inside of our shape. So like if we had some sort of grid, maybe I've got a triangle. That's not really the triangle I was going for. Let's try this again. Maybe I've got something like this. So this one would have 4 points. But we're not just going to be looking at our original starting shape. We're going to be dilating it. So that's multiplying our shape at each point of our shape by some constant. In our case, it's going to be integers, positive integers. So if we do this again, maybe my starting shape, and we're going to pretend that this actually looks like a nice little grid here, but maybe my starting shape is this little square. And so then the second dilate would be something like this, if assuming that this point is the origin. So that's what we're going to be looking at. And then the last thing is that this lattice point enumerator is going to encode the number of integer points for each dilate. So you plug in your dilate, and this formula will spit out the number of points inside. So let's do a quick example. My go-to is the unit square. So if we have this unit square, well, I think you can see pretty easily that the number of points inside of it is 4. And then pictured, I also have the third and fifth dilates. So you can count those out. You might notice pretty quickly that you can find a little pattern here. So we got 4 points, and then 16 points, and then 36 points. And in general, you'll notice that this is t plus 1 squared. Which is a nice little formula. And so you might ask, okay, is this formula so nice for other polytopes? And the answer is yes. And in particular, if you have a convex d-dimensional polytope, then the lattice point enumerator is a polynomial in T. So that's our dilation factor of degree D. So the dimension that your polytope lives in. At the leading term is going to be the volume of your original starting polytope, and the constant term is going to be 1. So if we multiply this all out, we can see that t plus 1 squared gives us t squared plus 2t plus 1. So this volume of the unit cube is just 1. So that's our leading coefficient there is 1. Our constant term is 1, polynomial in t, and the degree is 2, which matches our dimension. Okay, that's very nice. So now let's look at a specific, actually, before I move on, what questions do you have? All right. And if I'm going too fast, feel free to ask questions to slow me down. This is, I guess I know this, at least this part pretty well. All right. So we're going to now focus on a very specific kind of polytope. And this one has some nice Ehrhart theory around it, which is why we're looking at it. So this is called a zonotope. And a zonotope, there's a couple different ways that you can think about it. One way is that it's a projection of a cube. Another way that you can think about it is it's the Minkowski sum of line segments. And so here's this definition here. It's maybe a little bit easier to see with pictures. So for instance, we've got, let's look at this octagon here in the middle. So we've got these 4 generating vectors. So we kind of take each of them, and the Minkowski sum is like you kind of add up the vectors. It's this pointwise sum. So then you get this part, and then these two would give you maybe this square. And now lastly, if I take this guy with this part, this will give me this part over here. And then now maybe I need like those two. So then that would give me this. And then those two would give me this one. And then lastly, you've got these two here, so which would give you that. So that's kind of, maybe I should have used this one here too. But yeah, so we get this we get this octagon here. You can do similar constructions for all of these. So these are zonotopes. This is what we're going to be looking at. And one of the reasons that we're going to be looking at them is because we have this nice breakup result. And so as you saw, we were kind of constructing them using these generating vectors and kind of breaking them up in that respect. And so it turns out that every zonotope can be tiled using half open parallelepipeds, which are formed by taking linearly independent subsets of these generating vectors. So in 2 dimensions, let's take that hexagon that we had here. We can write this hexagon as our 3 generating vectors are U1 in pink, U2 in teal, and then U3 in dark purple. So now if I just take U1, my first goal is to tile this using half open parallelepipeds. So we can do that. We take this starting point here and then half open line segment. And so that takes care of U1. So now if I add in U2, now I'm going to have 2 half open line segments, each of which are corresponding to the particular generating vectors. And then I also need this parallelogram in the middle, which is spanned by both of them since they're linearly independent. And so that's half open. And you can see that if you kind of squish it all together, you're going to get this whole parallelogram here. Now, if we add in the third vector, this dark purple one here, and we're in 2 dimensions, so obviously a group of 3 vectors can't be linearly independent. And so that means that we can take at most sets of 2, and we do want each set of 2. And so adding in this third vector now is going to give us 3 half open line segments and 3 half open parallelograms. And we don't have any sets of 3 stuff, and we still have the little starting point. And again, we can squish it all together, and that's going to give the nicely filled in hexagon. And so this theorem is that you can do this for every zonotope, which is really nice. And especially since we're counting up the integer points inside of this, each integer point can only live in one of these half open parallelepipeds. And so this is our next result here by Stanley, which is saying exactly that. If you want to compute the Ehrhart polynomial, the lattice point enumerator of a zonotope, all you have to do is look at the half open parallelepipeds. So if we bring up this octagon here, here's a zonotopal tiling. You can tile it multiple ways. Here's the one that I've chosen. And now if we kind of break it up, you'll see that each of those integer points is in precisely one of the half open line segments. So essentially the 3 things that we'll need to compute for calculating the Ehrhart polynomial of a zonotope is we need to figure out which sets of the generating vectors are linearly independent. We need to figure out what the relative volume of the corresponding half open parallelepiped is, and we need to know the size of the set. And so since our vectors are linearly independent, the size of the set of vectors is going to be precisely the dimension that the shape lives in. So that's 3 things that we need. We need which generating vectors are linearly independent. We need the number of them, which is to say the dimension, and we need to know the volume. So those are the 3 things that you'll need to remember moving forward, because those are the 3 things that we're going to want to compute in order to calculate the Ehrhart polynomial of the specific shape that we're going to be looking at. So the specific zonotopes that we looked at for this project come from the classical root systems. And if you're not familiar with those, that's fine. This is just how we're choosing our generating vectors. So there are 4 classical root systems here. There's also the exceptional cases, which we didn't do in this project. I'm pretty sure that there is someone working on doing something similar to this with those ones, but I am not a part of that project. So the ones that we're looking at are A, B, C, and D. And what we're going to be doing is choosing the positive roots. So in each of these plus minus, you just take the plus. And that's what we're going to be looking at. And so, yeah, we're choosing this. So here's for d equals 2, here's each of the what each of these will look like. And so we're just taking the zonotopes with these as the generating vectors. So we've got, note that type A is going to live in a dimension lower. And then, yeah, we have type B, C, and D. And so notice I'm calling these the integral permutahedra, because these ones right here have the origin as one of their vertices, and then we're just taking each of these vectors here as one of our generating vectors, and then computing the zonotope generated by those. Does anyone have any questions at this point? Cool. All right, so then this is one way that you can look at these permutahedra, but this isn't the way that everyone wants to look at these permutahedra. So some people will choose this definition here. Other people will want to look at these as formed by the convex hull of permuting some coordinates. So for instance, this is type C pictured here, and the coordinates that we're, the numbers that we're permuting are 1 and 2. And sorry, this would look a lot nicer if I could get this pen to work, but it must be out of battery or something. So yeah, if you take all the permutation, so this is type C is signed permutations of 1 through D. And so you can go through and you can see that each of those vertices lines up with that definition. And if you look at these two polytopes, you'll notice that they look essentially the same, except they're shifted a little bit. And since we're interested in counting the integer points inside of our polytope, shifting it a little bit and keeping shifting it by an integral vector isn't going to change anything, because we're still going to have our nice little integral polytope there. But unfortunately, that's not always the case. So for instance, this is type B on the right, and the coordinates that we're permuting, we're taking signed permutations of 1/2, 3/2, 5/2, etc. And so that it's going to be half integral, but unfortunately, it's not going to be integral. And you might throw up your hands and say, "Oh, everything we've done so far relies on having integral vertices, and now this doesn't. So what can we possibly do?" So the good news is that we have something similar for rational polytopes, which is to say, if we have a rational convex d-dimensional polytope, then our lattice point numerator is no longer going to be a polynomial, but it's going to be a quasi-polynomial. If you don't know what that means, I'll define that on the next slide. But it's still in T. It still has degree D. We have this new thing, which is the period, and that's going to divide the least common multiple of the denominators of the coordinates of our polytope. And I believe that this is sometimes referred to as the denominator of the polytope. So what you do is you look at all of the coordinates of the vertices, look at the denominators, and then take the least common multiple. And then this period thing is going to divide that. All right, so quasi-polynomial essentially cycles through polynomials. So there's a couple different ways that you could look at this. This is my favorite. It makes the most sense, I think, with what we're doing. So we've got where k is the period, we're going to cycle through k polynomials, which depend on what t is mod k. And so this definition might seem a little abstract if you haven't seen it before. So let's look at a quick example here. These are some dilates of the integral type B permutahedron and the standard type B permutahedron. And so on the left side, we've got this integral case. And so let's see if I can write this out. So we've got, here's our first dilate. And okay, the first dilate over here, we've got 12 points on the left, 9 points on the right. So obviously those ones are going to be different. But now let's look at this second dilate. So this one over here and this one over here actually are going to have the same number of points inside, because if you look closely at the one on the right, you'll notice that the vertices once more are integral. And similarly for the fourth dilate of each of them, we once again get an integral polytope. And so what you should expect then is that when t is even, that the part of the quasi-polynomial that corresponds to t being even should match the Ehrhart polynomial of the just integral permutahedron. But then you should expect to see that the odd dilates give a different polynomial. And so for the one on the left, we're going to have 7t squared plus 4t plus 1. Again, you'll notice that this matches all of what we said. If you look at our original shape, you can see that the volume is 7, and then a polynomial in t of degree 2, constant term 1. So we should expect this to carry through for the integral, or sorry, the even dilates, but then for the odd dilates, we have something a little bit different. We still have this 7t squared, and so it does turn out to be the case that your leading coefficient will be the same. Oops, sorry. But we don't have this constant term 1. The middle term is different. So the question is like kind of what happens between the even dilates and the odd dilates. Does anyone have any questions at this point?
Yeah.
Oh, you go first.
Oh.
Okay, so on this example, could you tell what is the period here?
Yeah. So the period in this case is 2, because we're cycling between 2 polynomials, and that actually makes sense with our polytope here, because this actually has half integral vertices. So all of the denominators of each coordinate is 2. And so at the very least, it should divide 2, which gives us the option of 2 or 1. And since they are different, since we do see different number of integer points, we should expect to see 2. It does actually turn out to be the case sometimes that you have what's called period collapse, where your period will be smaller than expected. But yeah, in this case, it's 2, because we're cycling through the 2 polynomials. Good question. Thanks for asking that to clarify.
Okay, thanks.
Can you remind me where the Coxeter groups come in here?
Yeah, so this is with they're with the root systems. And so these right here are just the permutahedra that are formed from those classical root systems. Does that answer your question?
Yeah, that makes some sense. Thanks.
Okay. Any other questions?
Yeah, it might help to make a remark about the reflections, that the Coxeter group is a reflection group.
Yeah. So I guess in this case, so our reflections are like a lot. Sorry, this is bad, but we've got something like that. Assuming I can actually draw straight lines. But yeah, so each of our vertices, you'll notice that there's like 1 in each of those little cones there. And so yeah, you can do something very similar for each of the different ones, but the parts that you'll be reflecting over are a little bit different.
Yeah. Oh, I find it helpful to think about that the roots are the normals to the hyperplanes in the reflection group.
Mm-hmm.
Yeah, that's cool.
Any other questions? All right. So our next question then is kind of like, why is this happening? What's the difference between these two parts? So on the left, we have this integral one. Here's a zonotopal decomposition that we saw earlier. And then here's a zonotopal decomposition of the shifted one. Just as a little off remark, I tried to use different colors for the different permutahedra. So the integral ones are going to be blue, and the shifted ones are going to be purple, just to help distinguish those. But yeah, so going from this one to this one, we lose some points. We go from 12 points to 9 points. So where are these points? And okay, maybe this is a little bit harder to see in a two-dimensional example, but it's also a little bit harder to draw a higher dimensional example. So we will make do with this. But if we look very carefully, it's these three parts here. So the vertical half open line segment, the horizontal half open line segment, and then the vertex there are the three half open parts that don't have points anymore. So those are the same ones that are over here that do have points. And so what this kind of might hint at is, well, is it the case that if you shift these parallelepipeds, are they going to, what is it possible for them to like keep some of their points but lose others? So like, because that would add a lot of complexity, because then you'd have to figure out like, all right, we got this parallelepiped, we're shifting it around, which points is it keeping and which points is it losing? But it turns out to be the fact that it either keeps all of its points or loses all of its points, which is really nice, because then all we have to do is figure out which of these parallelepipeds are keeping their points and which ones are losing those points. That way we can toss out the ones that lose points. And so that this is essentially what we've got here. This function here is telling us sometimes we keep all of our points and sometimes we lose all of our points. But otherwise, we still have this linearly independent subsets. We still have this volume, and we still have this dimension here as the three other things that we need to calculate. So our additional question that we'll need to address at some point is when we shift our parallelepipeds, which parallelepipeds are going to keep their points and which are going to lose their points. So those are just four things that we need to calculate in order to get the Ehrhart quasi-polynomial of our permutahedra. And so to do that, we're going to turn to signed pseudoforests. And so just a couple of quick definitions here to get us started on a little bit of the graph theory that we'll need. A graph is a set of nodes and edges. Sometimes these nodes are called vertices. I'm going to stay away from using vertices because we already have vertices of our polytopes, and so having two sets of vertices could get a little confusing. So we've got nodes and then our edges, and the edges that we're going to be interested in allowing are links, which are edges between 2 points. So if I've got one node, two node, edge between those, that's a link. Half edges, which is you have one node and then an edge which doesn't have a node on the other side, and a loop, which you take a node and you put an edge that circles back to that same node on that. So those are the three types of edges that we're going to be allowing. But just graphs by themselves aren't going to be quite enough. We're going to need the signed versions. And so a signed graph is you take a graph, and then for each link and each loop, you give it either a plus or a minus. So notice that half edges are not signed, but links and loops are signed. So here's a few examples. So we've got a variety of graphs down here. One thing to note is that you can have two edges between the same two nodes as long as the sign on those two edges is different. So we can't have two edges between the same two nodes with the same sign, but if they have different signs, then that's going to be okay, and that's actually going to be something that we'll need. And then one more thing that we'll want to make a note of is this notion of balanced versus unbalanced cycles. So we say that a cycle is balanced if the product of the signs on its edges is positive, and unbalanced if it's not. So here, if we've got, for instance, this one here, we've got a negative times a positive, so that's going to give us a negative. So that particular cycle is going to be unbalanced. But then this cycle right here has a positive times 2 negatives. And so the 2 negatives are going to cancel out and give us positive. So that cycle is going to be balanced. What questions do you have about these graphs? And so the reason that we're going to be interested in these graphs is Zaslavsky created this nice correspondence between these permutahedra and these root systems and these graphs. So if we have a vector of the form EI minus EJ, where all these EIs and EJs are standard basis vectors. So for instance, if we have like, so this EI minus EJ would be like, we'd have like 1 in the ith and then -1 in the jth entry. And so then this would give us a positive edge. Now if I have the sum of standard basis vectors, so like something like this, then this will give me, why is it doing that? This will give me a minus edge between I and j. Now if I have just a vector by itself, so not adding anything to it, this will give me a half edge. So, and then lastly, we've got, if I've got this 2EI, then this is going to give me a loop, a negative loop in particular at I. So let's see a nicer drawn example of this. So for instance, my go-to example, because it's going to be the most interesting and easy to drop, is B2. And so for the positive roots of B2 are E1, E2, E1 plus E2, and E1 minus E2. And so here's the corresponding graphs of sets of either 0, 1, or 2 of these. So for instance, if I take like 1, 1 and 1, 0, so this right here is going to give me, this will give me a half, why is it doing that? Half edge at 1, and this right here is going to give me a negative edge between 1 and 2. So if we look, that's going to be this one here. And so we can do this for any combination. You could do 3 combinations of 3 or 4 as well, but to save space and to not have to draw them myself, I just went up through sets of 2. So yeah, so these are the corresponding vectors, or this corresponding graphs for the vectors that generate type B. We can also look at which half open parallel of hypa this corresponds to. So this right here is 1, 0 and 1, 1. So that's going to be this one here. Does anyone have any questions about this correspondence?
I do, Jodi, for the 2EI.
Yeah.
Why is it negative, or is it just by convention, or?
So another way of looking at this 2EI is like as EI plus EI, which gives a negative edge.
Right. Okay. Yeah, that makes sense.
Yeah, good. I always mean to say that, so thanks for asking. Any other questions? All right. All right, so let's see what's next. So what we're going to do with these is we're going to very carefully choose the ones that give us the stuff that we want. And so we're going to define the signed pseudoforest to be signed, or to be almost signed. It's an almost forest of almost trees. And so the things that we can have are signed trees. And then also you could have a signed tree, but it's like not quite a signed tree. Maybe it has a single half edge, or maybe it has a single loop, or maybe it has a single unbalanced cycle. So for instance, these right here are the three types of things that we're going to have. So here we have a signed tree. Let's see, I guess I can just use this. And then here would be a half edge tree, because it's a tree apart from the single half edge here. A loop tree we've got over here. And then lastly, this right here is going to be a pseudo tree. And it does have this cycle right here, but you'll notice that it's unbalanced. So you will notice that all of our cycles are unbalanced, because the only cycles that we're going to have are these unbalanced ones here, and these loops, which you can also think of as an unbalanced cycle. And just as a quick little notation, or to make it easier to talk about these things, we're going to say that a phi forest, so remember phi is one of our root systems. So a phi forest is a signed pseudoforest such that this G, which is our pseudoforest, equals, oh, let's see, did I change my way of describing this? No, here's our G of S. Okay, cool. I changed a couple things and I wasn't sure if I'd taken this out, but G of S is the graph corresponding to this subset S of positive roots. So this right here is going to be, we're going to say that a signed pseudoforest is a phi forest if you can build it from these signed root, or from these positive roots.
Yeah, I think it should be mentioned that those three possibilities are separately applied to each of the components of the pseudoforest.
Yeah,
so,
yeah.
So pseudoforest might have many single loops as long as each single loop belongs to only one component.
Right. Yeah, so that's a good clarification. So each connected component of our graph can have precisely one of these. As soon as you add a second one in, something breaks. So yeah, thanks for that remark.
Could you elaborate on that? How do you mean by something breaks when you have multiple?
That's actually going to come up on the next slide. Yeah, so the graph itself isn't going to break. Like it's still a very nice signed graph, but we won't have this nice linear independence result. So in particular, we get that the linearly independent subsets of our positive roots are precisely the graphs whose are precisely the vectors whose corresponding signed graph is a signed pseudoforest, or is a phi forest. And so we do particularly need this, that we've got these almost trees. So if, for instance, I had this loop in addition to this stuff over here, then I wouldn't get that the vectors are linearly independent. And kind of the reason, the way that you can kind of think about that is if you have the nodes correspond to kind of the dimension, and then the edges correspond to the vectors. And so if you have a tree, then you have one more node than edges. So that's kind of like a d-1 dimensional shape. And if you have something like one of these that has this cycle, then it's no longer a tree because you've added in a single edge. And same with this one, you've added in a single edge. And also with this, you've added in a single edge. So then we have precisely the same number of nodes and edges. And so that's going to be like kind of a full dimensional subset. And so if you add another vector on top of that, you're not going to be linearly independent anymore. And so let's look at that with this here. So now you get to see the second reason why I only chose subsets of two vectors, because in dimension 2, as soon as you add in that third vector, you're going to get something that's not linearly independent. And so each of these correspond. So it turns out actually, because we're in dimension 2, any combination of two of the positive roots is going to be linearly independent, and so each of the subsets is fine. Once you get to 3 dimensions, you won't have that, but again, a little harder to draw. And so we can go through and, like, for instance, this one is 1, 1, and 1 minus 1, so that'll be this guy here. But you can see that as soon as you add, like, maybe 1, 0 to this, you'll get a hexagon, for instance, and this hexagon is definitely not a parallelepiped. One other thing that we'll want to be able to keep track of the number of different types of components. And so we do that, just the letter in the front indicates which type it is. So TC of G is going to be the number of tree components, and then the others are going to be similarly defined. And one of the reasons is kind of ties into dimension. So this number of tree components here, I already said that the number of nodes and edges can tell you something about the dimension. And so since we know that that in a tree, the number of edges is 1 less than the number of nodes, so that's like the number of vectors is going to be 1 less than the total number of vectors that we could possibly have, which means that if we have some subset of our positive roots, and then we look at the corresponding graph, the number of tree components is going to tie into the dimension, in that every tree component is has 1 less vector than necessary to be full dimensional. And so to calculate the total dimension, you take D, which is your number of which is your starting dimension, and you subtract the number of tree components. So right now we actually have 2 of the 3 things that I said at the start that we needed in order to compute the Ehrhart polynomial, because this right here gives us the linearly independent subsets, and then knowing the number of tree components of each graph tells us the dimension. So the only thing that we have left here is the volume, which we can have here. So the volume corresponds to the number of loop tree components and pseudo tree components. So let's see what that looks like. So here we've got our type B. If we look at these top ones here, because these right here are going to be the full dimensional ones. So here we have 2 tree components. So our dimension is going to be D minus 2. So that's just this vertex right here, which makes sense. And then each of these ones has 1 tree component. So D minus 1, these are our 1-dimensional parts. And these are actually just going to be the generating vectors themselves. And then these are going to be our 2-dimensional components. And this one right here is the only one that has either a loop tree component or a pseudo tree component. So what we should expect is that all of these contribute 1 integer point, because they don't have any pseudo tree components or loop tree components. And we should expect that this one contributes 2 points. And since this one right here corresponds to this parallelepiped right here, this actually turns out to be exactly right. So if you look carefully, you can notice that each of the half-open parallelepipeds has 1 point, except for this one right here, which has 2. So that gives us everything that we need for the Ehrhart polynomial. And this, back in 2015, was shown by Ardila, Castillo, and Henley, where if you have we're summing over phi forests, because those are linearly independent subsets. Here's our volume, here's our dimension. And so let's see what this looks like for this here. Here I've got these parts here are are going to contribute t squared because they're the two-dimensional ones. So there's 5 of them, and each is contributing 1 point. So this is going to give us 5t squared. This one right here is going to give us 2t squared because it's contributing 2 points. Each of these is a one-dimensional part, so it's just going to contribute a multiple of t, and there's 4 of them, so we're going to have 4t, and this is going to be our plus 1. So overall, this is going to give us 7t squared plus 4t plus 1, which I might have written down. Nope, I made myself write it down. Okay, so but we already said this is going to be 7t squared plus 4t plus 1. If you remember from the start, this is exactly the Ehrhart polynomial that we had to start out with. Does anyone have any questions at this point? Cool. So then, all right, so we started out with these nice polynomials. Now and these nice integral permutahedra. Then we have the rational permutahedra. So which ones are rational? Because if you look at this picture, it looks like this one right here is the only one. So this is the type A, B, C, and D. So this one right here looks integral. This one looks integral. This one's rational. This one looks integral. So when are they rational and when are they integral? Because if they're integral, when you shift them, then we're done and they only have this polynomial. But if they're rational, then we need to do a little bit more work. And it turns out that types C and D are always going to be integral when you shift them. So in particular, the vertices of the shapes that are centered at the origin are going to still be integral. Type A depends on the dimension. So if D is odd, so in this case, D is 3, you're going to get something that is integral. But if D is even, then you're going to get something that's half integral. So for the next few slides, we're only going to be looking at the root systems that correspond to these half integral polytopes, which is for types B, and for types A, where D is even.
Jodi, just to clarify,
Yeah.
The B, C, and D are 4-dimensional and A is not, right?
Yes.
Okay.
Yes. Yeah. So A is a little bit funny in that respect. But yeah, if you remember back to the first slide, like the type A was like, or towards the start, type A 2 minus 1. Go away. Why is it? Okay, we're gonna. Is it still here for everyone?
Yes, we can see that you have an update available.
Great. Awesome. Love updates. Not in the middle of talks though. All right, so for type A2, it was something like this. And this was the point 1 minus 1. Okay, it likes to select it. We'll just leave that then. So yeah, if you shift this one, you'll get something that's half integral. So yeah, so we still have all 3 of the things that we needed for the Ehrhart polynomial. So remember, the 4th thing that I said we would need to compute or need to figure out is when we keep our points and when we lose our points when we shift. So let's look at these 2 parts again. We said that we had, okay, let's switch this. This one, and this one were the 3 parallelepipeds which lost their points. We can see here that those 3 don't have points anymore, but everything else still does. So what's the difference between those 2? And it turned out if we look at the signed pseudoforests again, it'll give us the information that we need. It's a little bit complicated to draw and explain. I do have some slides at the end that show pictures of one example of how this works. But it turns out that if every tree component of your signed pseudoforest has an even number of nodes, then you keep your lattice points. But as soon as you have a tree component that has an odd number of nodes, you lose all your points. So now we're going to call these I think the even trees and odd trees or something like that. But this actually gives us everything that we need for the Ehrhart quasi-polynomial, where the only difference is now we have this subset E of our phi forests, and we want even number of nodes. But the volume computation is the same. The dimension computation is the same. One thing to note is that I didn't write here the plus L of t because type C is the only one that has the loop tree component. So we tossed that since we don't have type C here. But yeah, so the only difference is in what we're summing over, and it's very nice and easy to write down. But let's see what this looks like for our favorite go-to example of B2. So we're looking for the graphs that have the tree components that have an odd number of nodes, and we'll keep everything else, but we want to toss out those ones. And so, well, these are two trees that have an odd number of components, so we definitely want to toss that one out. This one has an odd number of components, and this one also just in this single node. The couple others, these two are tree components, but they have an even number of nodes, so we'll want to keep those. So it's these three right here that we'll want to toss out. And we had 3 parallelepipeds that lost their vertices, so do these actually match up? So let's first write down our Ehrhart quasi-polynomial here. So remember, we said for the even dilates, we're going to get the exact same thing because nothing changes. And up here, you'll see we still have our 7t squared. And over here, we're going to have 2t. And then this part over here is going to give us another 2t plus 1. And so if you remember, the Ehrhart polynomial for the unshifted version was 7t squared plus 4t plus 1. And if you remember back from the start, we did have 7t squared plus 2t. And so that's what we're going to have here. And now if we look at this shape, let's just make sure that these do correspond with the parts that lost their points. Well, this one right here is no vectors, so that's just this vertex right here, which is definitely one of those. This one right here is the vector 1, 0, which is right here. And this one right here is the vector 0, 1, which is right here. So these are precisely the ones that lost their points.
I have a question.
Yeah.
So what about that leftmost purple one? Doesn't that have 2 components with 1 vertex each?
This one right here?
I can't see what
the leftmost one.
Oh, this one here?
Right.
Okay, yeah, so this is one graph. So what this looks like is this is 1, 0, 0, 1. Sorry, it's going over top. So that would be this parallelepiped right there.
I guess I'm still a little confused. I thought the condition was that every component has an even number of nodes.
Every tree component. So these ones are half-edge trees.
Okay.
Yeah. Yeah, and kind of the reasoning behind that is the tree components are the ones that bring us down a dimension. And if you have a full dimensional shape and you bump it around, it's not going to lose its points because it's still full dimensional. But if you have a lower dimensional shape, then moving it around, you can move it off of the lattice. But yeah, that is a good thing to clarify. Thanks.
All right, thank you.
So that essentially means all of the top purple ones that you'd ever have for any example, you always include all of them. You don't have to worry about odd or even.
Right. And kind of the reason for that is if you again look at the tree components, they won't have any tree components because they're going to be full dimensional. And again, the tree components are the only ones that we really need to look at. Oops. Thank you very much for listening. And here's our references.
All right, let's thank Jodi. It was a nice talk. Are there any questions for Jodi?
Yeah, I have a question. How robust is this analysis to changing the lattice, right? Because it would be natural, especially in type A, to think about the root lattice instead, or the weight lattice. instead of
That's
ZN?
yeah, that's a good question. I'm not completely sure because I haven't thought about that really at all. But I think as long as you're able to come up with a similar type of graph description, you could probably do something along these lines. This will definitely work for like other like combinations. Like if you just have like various like EI plus EJ, EI minus EJ, and take various subsets of that, this should still work for the zonotopes generated by those. If you have like EI plus EJ plus EK, then that I'm not sure how that one would work either, because then you've got like one edge that's supposed to have 3 different nodes that it attaches to. And yeah, I'm not sure. You'd need some sort of comparable description for the graph.
All right, thank you.
So I was just wondering, if you have a bigger period, would the pictures look different? And like how can you tell that something has a period that is not 2?
Yeah, so that all depends on the coordinates of your vertices. So my vertices were all either had denominator 2 or 1, which means that they're at most half integral. But if you have a denominator of 3 or higher, then your quasi-polynomial is likely to have more parts to it. It can't. There's not like a complete like you can't completely derive this from just looking at the denominators, because there is this thing called period collapse, which means that you could potentially have something smaller than expected. But generally, that's a good place to start. It does for sure give you an upper bound.
Do you know why sometimes you would have a smaller than expected period?
I don't. I know that there are people who are very interested in learning about that, though. So yeah, if you look up period collapse, you can see more about that. But I know very little about why that would happen.
Okay, thank you. Just one little comment. You said you were gonna color coded the integral and the rational ones. Well, at the bottom you have 4 things, and then you said one of them is rational. So maybe you should change that too.
Well, but you see, all of these are the shifted versions.
Oh, and that's by definition the rational one.
The ones that could be rational, yeah.
Okay, thank you.
Yeah, so yeah, maybe it would have been better to say that these are the blue ones are the standard. So I think we had this pi with a z, and then these ones are just pi.
So you, Jodi, you made a comment very early on about, so you said somebody was working on the classical root system.
The exceptional cases?
Yeah. Can you tell us a little bit more about that? Or
all I know is Federico handed the problem off to one of his students.
Oh, okay.
So
Makes sense.
yeah, Federico would know more about that than I.
Are there any other questions for Jodi? All right, before we thank Jodi one more time, let me invite you all again for next week. Next week, we'll have Venkatesh talking to us about covering symmetric subsets of the cube by affine hyperplanes. So I hope that you'll be able to join us then. And with nothing else, let's thank Jodi one last time.
Hey, very nice. Thank you.